Great. Let's continue with the NFA. We were doing some examples of proving what the language of a NFA is. There's some on the homework about DFAs, which are, in my opinion, quite a bit easier because of the rule of the property about the deltas for NFAs. So we are going to do a couple more of these NFA proofs. I got one, and then I have one for you all to try, and then we'll go into something a little different. So let's talk about proving NFAs accept some strings. That's the thing that we're trying to do here. And the important step in these proofs, so these are always going to be proofs by induction, and the key step in these proofs is always something about delta star of a delta star, that kind of a thing. When you write that rule for DFAs, it's a lot simpler, unfortunately, than the corresponding rule for NFAs, but I will remind us. The rule says, and this is like the basic rule about delta star, and it says if delta star of S and X contains the state T, then delta star of S and XY contains as a set delta star of T and Y. All right. This is weird and more complicated and like easy to mess up when it comes to remembering this correctly. Weird and more complicated than the corresponding rule for DFAs. But anyway, this is the property. I'm going to sort of put this in a box. The idea behind this is basically about what happens when you start somewhere and you do X followed by Y. And what it says is, well, if you start here and you just do X, and if you can get to state T, then all the states you can get to from T to Y, those are part of the states you can get to from S and doing X followed by Y. It is confusing, but unfortunately this is like as simple as it gets in terms of how you can express this rule. There isn't really a better way to say it. All right. So anyway, this is the basic rule. Let's see if we can do, like I said, I have one more example, and then I have one for you all to try out. So let's try this here. I got STU. All right, this is my NFA. You can see there are two outgoing A arrows from S. That's what NFAs are all about. And no outgoing arrows, A arrows from T. All right, so first of all, a typical, homework or a test question about this, I would say something like, first of all, tell me what is the language accepted by this NFA, and then prove that all of those strings that you said are actually accepted. So here, this accepts any string like, what do you think? Give me like a formula, yeah?
A, B to the n.
A, B to the n, yeah, that's what I would say. This one is fairly straightforward. You got to do A first in order to arrive in the accepting state. You got to do A first, and then you can do a bunch of B's if you like. So this accepts any string like A, B to the n, where n, of course, is allowed to be 0. Okay, great. Let's try and prove that. So formally speaking, how I would write this, formally what I would like to prove is something about delta star of something, something equals something. Anyone think you can fill in the blanks here? What specifically am I going to be trying to prove here? Yeah?
S, comma, A, B to the n.
Yeah?
And then contains T.
Yeah, great. Yeah, I shouldn't have said equal. So you could, if you like, say equals the set of T, but really that's not, you don't have to, it's better to write it this way. Contains as an element T. All right. This is what it means to be accepted, is that when you do this delta star, of course, delta star, the result will be a set, but when you say the string is accepted, what you mean is that this set contains T as an element, because T is the accepting state in this case. Excellent. All right, let's see if we can prove that then by induction. So we are going to do induction on N as always. All right, we begin with the base case, which is n equals 0. So I want to show that delta star of S a b to the 0 contains T as an element. And, as usual, this just sort of turns out to be obviously true if you write it properly. So delta star of S and a b to the 0, of course, this is delta star of S and A. And what is that? We should be able to say just specifically what is delta star of S and A? What do you think? Yeah? T? Anything else? U2. Yeah, I would say actually this is T and U. From S, if I do A, I can go to T or I could go to U, right? I don't know if this worries you, but it's true. This should be the set of T and U, all right? Remember, the answer of this kind of delta star is always a set. So even if we're just T, you would say the set containing T. But actually, in this case, it's both T and U. And what I'm trying to show is that this contains T as an element. But it does, right? It has T and U. So certainly it does contain. So this is still true, right? It does contain T as an element. And so that's it. We have demonstrated the base case, right? It's not necessary that this equal just T. It's just it has to have T as one of the elements, which it does. All right, and the inductive case. This is the hard step. I mean, as usual, it's hard for these NFAs because we have to use that weird property that I said at the beginning about the S's and the T's. So anyway, we begin with the induction hypothesis. We're going to assume that delta star of S, A, B to the K contains T. And then I want to show delta star of S, A, B to the K plus 1 contains T. All right? And we have to, so knowing that in all of these examples, the main tool is this thing which you see in the box up there. And I hope you can still see that on your paper somewhere. That's the main tool that we're going to use. Really, what it amounts to is here, this x followed by y. You have to decide for yourself in your proof what's going to be the x and what's going to be the y. All right? And when I look at this, and this I think is not a mystery because we've done similar things before. When I see this, I would like to break this up into an x and a y, where the x, well, I'm going to break this up like this. A, B to the k, followed by one more b. That's because, why did I do it that way? It's because I know something about a, b to the k is part of the induction hypothesis, right? From a naive point of view, you might look at that and say, oh, maybe I'll split off the A separate from the B to the K plus 1, but actually this is not what you want. The induction hypothesis says something about A, B to the K, so that's the part that you should try to split up into these two parts. So when I plug into the big weird thing in the box there, that's going to be my X and that's going to be my Y, right? And you will notice when you look at this, what this says is delta star of Sx contains T, right? That second thing here is my X. And so actually this is convenient to use just in the box formula up there, right? So I will say, starting with the induction hypothesis, we know that delta star of S, A, B to the K contains T. So by the thing in the box, I am using that as like the if part. That is, what they call the hypothesis. If this is true, then this is true. So remember, that right there is my X, right? So we do indeed know that delta star of Sx contains T. Then the rest of that thing says delta star of S comma xy, which in this case is AB to the K B, contains as a subset delta star T comma Y, which is B in my case. All right? This, in my opinion, is fairly complicated to figure out how to plug everything in properly, but I hope that that made sense. Anybody got questions about this? I'm going to have you try one in a few moments, so you'll find out real quick how you like it. All right, you have to plug everything in properly to the weird formula at the beginning there. All right, anyway, are we done here? Where do we go from here? I have this delta star of ty, but this we can just look at the picture and say what is, sorry, I wrote y. I should have written b, right? Y is like the name of the variable as it appears in the box. Sorry about that. B is what I meant to write, which of course, I mean, that's what I'm calling y in the box, but B is what I should have written there. Okay, anyway, what is delta star of t comma b? That you can just look on the diagram. This just means if I'm in state t and I do b, where does it go? And the answer is just b, right? In state t, the only thing you can do with a b is end up back in state t. So this, now technically speaking, this is the set of just the state t. But anyway, that contains t as an element. All right? And so this is really all that we need. We have really demonstrated. If you start with this, it'll say a b to the k plus 1. Read it all the way across, contains t as an element. So I will just write that to finish it off all nice. A b to the k plus 1 contains t. And that's what we needed to show. You can still see it at the top there. That's what I wanted to show. All right. Any questions about that one? It's a little confusing to use the appropriate delta star formula, but that's how we do it. All right, I got one for you all. See what you think. See how you like me now. About this one right here. Okay, I got, again, your job is, first of all, decide what kinds of strings are accepted, and then prove that those strings actually are accepted. All right, there you go. See what you think about that. Feel free to talk to your friends, but you all chose your own tables, so feeling like maybe you don't want to talk to each other. It's all right, I guess. You all seem nice to me, though.
there should be an N somewhere.
Oh, yeah. I feel it.
So you have to do A. Well, first of all, you don't have to do A, B, L.
Yeah.
You just go straight here. But there's only going to be one B, right? Yeah, I would say you do this as many times as you like. So there's a N in both of that. And then a B. That's looking good.
All right.
What'd you get for your language? Like that. So I think it's a little more specific than that. So this means X can be anything. Then you can take anything to the nth power. But it is, you have to do A, then B, then A, then B. How's it going? Good, that's good. Good job. You would do something like A, B to the N. But it's kind of, yeah, right. It'll work.
This is what I got for the language. I thought some people worked it out. That's how you should begin with your
A, B to the N. B. How's it going? Yeah, yeah, that's good. Today's case. No, because this A, B is kind of like coming together. So in terms of the design, it was like A first and then B stuff.
Okay.
How's it going? It is looking good. Yeah, yeah. Is everything okay? Yeah, that's great. Still good here? Yeah, yeah, that's. How's it going? Yeah, that's right. Yeah, I would say this is a good idea. I would say for the sake of using the induction classes, you want to use the cadence. So click it in. And then get around. How's it going? I mean, if you're using this as written, then it's first. You can do either way. It should work out. So I would call that A, B, I would call X, or X, and I would use it. And so you have to first demonstrate this like if it worked. We would just say delta star of S, A, B, T, for, well, not T, but U.
I'm going to see if we can work this out. I see some people making good progress. Some people worked it all the way out. This, like I said, these are difficult. First of all, let's state what we want to prove here. I'll write it as a little theorem just for fun. Formally speaking, I'm trying to show that delta star of S and AB to the NB contains U, right? And pretty much everybody, I walked around, pretty much everybody worked out the base case. So our base case is n equals 0. I want to show that delta star of S and AB to the 0, B contains U. And this, of course, is equal to delta star of S and B, and that equals the set U, which contains U. So this is the base case, works out nicely. I think that everybody worked that one out all right. Now the induction case is a little tricky, as always. So we assume delta star of S AB to the K, B contains U, and I want to show the same but K plus 1. All right, and I look at this string here and I decide to split this up into like an X part and a Y part, and you have to do it in such a way, like in order, of course, there are many ways that you could split this up, but in order for it to be like a useful way, sort of one of the parts you want to equal this so that you can actually use the induction hypothesis. So the proper way to split this up into two parts would be AB first, followed by AB to the KB, right? And make sure it has to be written in this order. This AB first. I saw some people put like an extra AB on the end, on the right end, which is not right. It has to be over here. You can't just rearrange these things willy-nilly, as they say. So this I'm going to call my X. This is going to be my Y. All right? So when I plug into my, my sort of thing in the box, maybe, would you mind if I just copy this down here so that I can have it straight? This is good to have on hand when you're doing these. Maybe I'll shrink it down a little. Nope. Whoa, yeah. Okay. So in here, I'm using, this is my X and Y. We also have to decide, like, what are the S and the T that are appropriate to use here. Of course, in my example, there are states called S and T, but these ones over here are like variables, and you can use whatever you like over here. All right. And the if business, it says if delta star of S and X contains something or other, like that part for me will say delta star of S and AB. But what is delta star of S and AB? When you look at the diagram, starting in S, AB just goes back to S, right? So this actually contains S, right? That's the if part that I'm using. So when I'm sort of plugging everything into the various pieces in the box, I'm using S as S, but I'm using S as T also. Remember these S and T, they are themselves variables, and so we can sort of plug whatever we like in for the S and the T, all right? So here, I will say something like, this is what I'm starting with. So I could begin by saying, sorry, let me just get rid of these guys. I'm going to write it again. So I'll say we know delta star SAB contains S. In fact, it equals the set of S, which contains S. And so, by the thing in the box, so then I'm using this thing in the box where the T is S, the X is AB, and the Y is AB to the KB. So this will now say delta star S XY, that is AB, AB to the KB, contains delta star T, which is S, Y, which is AB to the KB. like that. So I have successfully plugged into the stuff in the box. This is weird and confusing in my opinion. So if you feel the same way, don't worry about it. But, I mean, you still got to do it, so worry about it a little bit. But it is weird and confusing in my opinion. All right? Anyway, where can I proceed from here? Anyone see where this is going? I want to try to, work with this now, try and simplify this if we can. What do you think? Anybody want to say it? I don't want to hear it from you. Somebody else, I appreciate. Sometimes I feel like, if you don't mind us talking about our feelings briefly, I feel like sometimes you guys know things but don't want to say them. I don't know if that's true or not. I thought about maybe I should just go around and call on people. Would that be all right? I know people don't like that, but I feel like everybody knows what I want you to say. You just don't want to say it. What do you think? Where do I go from here? Anybody feeling it?
You just
Thanks.
said it equals the set of you?
Yes, kind of. How do you know that?
Because if you do AB to the K, B, and the NFA, then you get the you.
Yeah, that's true. Although that's in a sense using what we're trying to prove, because that's the whole point of all of this proof. But I would say this is the induction hypothesis, right? The induction hypothesis mentions this set exactly, and it is saying that this contains U as an element. And so this is just by the induction hypothesis. That contains U, which is what he said anyway. All right, and that's really the end, right? So if you read this all the way across, this is a B to the K plus 1 followed by B, and it contains U, and that's what we needed to show for the induction step. So reading this all the way across, delta star S, AB to the K plus 1, B contains U. This is what we had to show in this induction step. All right. That's all I wanted to do for those. These could be a lot harder, but I think we're going to sort of leave it at this. So you will have some practice with these on the homework to see how you like them. Any questions about that? I think 30 minutes on this kind of a thing is plenty of time for today, because I want to talk about something else about NFAs. All right, let's move on then. So enough induction proofs for a while at least. Let's get back to some more down to earth, perhaps, constructions involving NFAs. The big question which I would like to pose concerning NFAs, which we will answer, I suppose, this time and next time together. What kinds of languages can be accepted by NFAs? Right? What kinds of languages can be accepted by NFAs? This, of course, we talked about this question concerning DFAs, and we had a name for those languages. They were called the regular languages, right? A regular language means it is the language of some DFA. But NFAs, they are like DFAs, but they have more stuff you can do, right? So at least in theory, it seems that NFAs, maybe there are more languages that you can get by using NFAs, because NFAs are allowed to do more stuff than the DFAs are. One thing that I can say just as a preliminary answer to this question would be certainly any regular language can be the language of a DFA. NFA. Any regular language can be the language of an NFA. That's because regular language, remember, this means a DFA language. Right? Any DFA language can also be the language of an NFA because if anything, NFAs can do more, right? Like every DFA already counts as an NFA, but NFAs are allowed to do more kinds of stuff. But they can certainly do all the same stuff that the DFAs do, all right? So certainly any regular language can be the language of an NFA. The more interesting question is the other way around. Are there special languages that you can do on NFA but not DFA? That's the real question here. And I will tell you the answer in kind of a long-winded way, but there is a construction about this. It turns out, actually, there are no languages that can be accepted on NFA but not DFA. Right? So even though the NFA seems to have more capabilities, like there are more things you're allowed to do with the NFA diagram, it turns out that actually those extra capabilities don't actually result in any kind of extra, more interesting kinds of languages. They are still just computing the same kinds of languages as DFAs. So the way that we're going to explain this is actually, all NFAs can be converted into equivalent DFAs. And there is a procedure for doing this, just using the diagrams, which is not all that complicated, although it is something you have to be kind of careful while you do it, but it's not all that hard to do. All NFAs can be converted into equivalent DFAs. Another way that this is sometimes called is NFAs can be simulated with DFAs. That is, if I show you an NFA, actually it is possible to convert that NFA back into a DFA, which is equivalent to the original NFA. Like, for example, here's an NFA. This is a cute example NFA that we have talked about before. With epsilons like that and 3 states. The language of this, so what kinds of things are accepted? Well, you could just, starting here, you could just go up here and do some A's. That would be accepted. Or you could go down here and do some B's. That would be accepted. Or you could actually go up here, do some A's, then go down here and do some B's. So the language here would be strings which consist of some A's followed by some B's, but nothing else. So you can't have like more A's after the B's. So this here, the language is, you would write it like A to the N, B to the M, right? It has some number of A's first, followed by some number of B's. And those numbers can be 0, so you could have only B's if you want. All right? This is an NFA. But actually, that NFA, it is possible to make a DFA for the same language. So this NFA, it's actually equivalent to, I worked this out ahead of time. I'm sure that any of us, given enough time, could work out the details. It's a little more complicated, but this is a DFA accepting the same language. That is a DFA, which also accepts the same language, A to the N, B to the M. All right? This DFA is more complicated than the NFA. It has more states and whatever. But what I would like to describe, and I think our remaining time today is enough to do a simple example. There is actually a procedure by which you can start with any NFA, and by doing some fairly simple tricks with the diagram, you can convert this picture into this picture. All right? You can start with, this one is equivalent to a DFA. That's the point. We have an NFA here. which does the same thing as this DFA. And what I'm here to tell you for the next 13 minutes is this is always possible to start with any NFA. You can always convert it into a DFA like this. Hello, we're almost done. All right, how do we do it? I'll give you kind of the short version, and we'll do some more examples of this next time. In order to do this, it's kind of like that thing that we did with combining two DFAs in pairs, that sort of a thing, although you're not combining two things. You just start with one thing here, and you do something to it to create this DFA. Here's how we do it. Give names to the states. Anyway, this is referred to, the name of this is called the subset construction. The subset construction, all right? That thing about the pairs was called the product construction because we were making pairs of states. This is called the subset construction because we are going to consider all sets or subsets of states. Check it out. So I'm just gonna do that same example as a little model with the epsilons. I'm gonna give names here. Maybe I'll just call them Q0, Q1. This is how our book often likes to name the states. Q2 down here, epsilon over there, and a looping B, right? Okay, so I am going to create, from this, I'm going to create a DFA. I'll try and write a few words about how this goes. Build a DFA whose states are sets of states from the NFA. All right. This, after all, is kind of the main difference, formally speaking, between the NFA and the DFA, is that when you do the transitions in the NFA, you get sets, not individual states. But we can make a DFA where all the states represent sets, all right? And the starting state in our DFA is a set which consists of the original starting state from the NFA. And there's a little technicality here. The starting state in our DFA is the set of all states reachable by epsilons from the NFA starting state. All right. So when I draw my DFA, it will begin at the set of Q0 and also Q1 and also Q2. That's because any of those states is actually reachable from the beginning, even before you read any letters from your string. All right, so my DFA that I'm going to draw here, maybe I'll just draw it and then we'll talk about the details in more detail next time. The state that I start in is the state which is a set, Q0, Q1, Q2. All right, this is my starting state in the DFA. And then we have to draw our arrows. All right, so since this is a DFA, it has exactly two outgoing arrows. There's an A arrow and a B arrow. And where does the A arrow go? So from here, the A arrow should go, where are all the places you can get to if you start in any of these states and do an A arrow? All right. The answer is I could get to Q1 if I did an A starting from Q1. I could get to Q1. I think I could not get to Q0 if I were in any of these states and I did an A. It could not end me up in Q0, right? It could end me up in Q1. It could also end me up in Q2 if I did from here an A followed by an epsilon. All right, so the A arrow here will go to a state which is labeled as Q1 and Q2. All right. This arrow represents all the possible states you could get to, starting in any of these and doing an A, followed by epsilons perhaps, because you can always do epsilons. All right. You could end up in Q1 by starting here and doing A, or you could end up in Q2 by starting here doing A and then epsilon. You cannot, under any circumstances, end up in Q0 after doing an A. All right. What about the B arrow? Where could I end up after doing a B from any of these original states? I think the only place you could end up is Q2 after doing a B. It's not possible to finish in 0 or 1. So the B arrow will go to something which has only Q2. I'll just draw that down here. The B arrow, just Q2. All right? And we continue the diagram like this. We got plenty of time to finish this example at least. All right, let's do the arrows from the Q2 state down there. So from here, you ask, so for the A arrow, this means if I'm in state Q2 and I do an A, where could I end up? Look at the diagram. If I'm in state Q2 and I do an A, where could I end up? The answer is nowhere, I think. You can't go anywhere if you do an A here. That counts as a set, though. That would be the empty set. So there's going to be a state. Maybe I'll put it down here. The empty set. This is A. I was talking about A, right? There will be, typically when you do these examples, there will be an empty set state. All right? What about the B arrow from Q2? Can anybody say? From Q2, I do a B. What states could I arrive in? What do you think? Yeah? Yeah, if I'm in state Q2 and I do B, the only other state I could finish up in is Q2 again. So that is a looping edge. I'll put it over here so I don't get in the way. All right? Great. From the empty set, this is a DFA, so we need outgoing arrows everywhere. This is sort of a technicality, but the empty set state will always loop with A and B. That means if you don't start nowhere and you do A, where can you go? The answer is nowhere. And if you're starting nowhere and you do B, you get in nowhere. So the empty set, when you do these examples, the empty set state always has a loop with the A and the B on it. All right, almost done here. We have this state, Q1, Q2. I need 2 outgoing arrows from there. So I look, you have to be very careful when you do this, but what this means, let's talk about the A arrow. If I'm in either of these 2 states and I do an A, where can it go? Can it end me up in Q1? I think so. I could just go like that. Can it end me up in Q2? Also, yes, because I could start here and go A epsilon, and I can end in Q2. Yeah.
Can you also end up in an empty set?
No.
Like you epsilon to Q2 and then you use the A?
Yes. I see what you mean. I'm not going to write that, though. So let me just, what I said was that, right? I think this is what I said. Now, this is a good question. I think he's suggesting maybe it should say this, because sometimes you could do some kind of weird move where you get stuck, right? But actually, if you think about it, this doesn't really make sense to write that. What I'm supposed to be writing here is each time a set of states. And it's just all the possible states you can get to. This doesn't really make sense from that point of view. The fact is, I can get to Q1 or I can get to Q2, and there's nowhere else I can get to. And the way you write that is just this, not like that. So yeah, this is not a bad idea, and it is true some particular strings will just get stuck, but that just means they don't end up anywhere. It does not mean they somehow end up in the empty set state. All right, almost done. Q1 and Q2, that was the A arrow. What about the B arrow? From either of these states, if I do B, I think the only place I can end up is Q2, right? And so that looks like this. And I think my diagram is done now. All right? Last thing I have to tell you is how to decide where the accepting states are. And the rule, I will write down all the rules next time, but just for the sake of getting through the example, the rule is anything which was accepting on the original diagram, any set containing any of those accepting states becomes accepting on the new diagram. So this Q0, Q1, Q2 is accepting because it has a Q1 in it, and Q1 was accepting. And also it has a Q2 in it. So this one is accepting. This one over here, Q1, Q2, is accepting because Q1 is accepting on the original one, and also Q2. This one, Q2, is accepting because the original diagram had Q2 accepting, and the empty set state is not accepting because it does not contain any of the original accepting states. All right? And that is my DFA. And check it out. I find this kind of satisfying that this actually works. Look at this. This is my DFA. Can you hold that picture in your mind? Can you see that one at the very top there? Which I said this was equivalent to this other weird DFA. Feast your eyes on that. That's the same as this, right? I actually did come up with the same answer. I mean, it's drawn sideways or whatever, but it is the same diagram. And so, what I said before, I hope you agree, I hope you believe me now. There is a general procedure to start with an NFA like this and cook up this, sort of out of nowhere. It's not really out of nowhere, but it is a, I suppose, slightly complicated procedure that you can go through. All right, so in this way, so this is how we converted the NFA to DFA. All right, aren't we proud of ourselves? We're going to do some more examples of this next time. But this is why when you talk to people out, you know, on the playground, in the club about finite automata, often people will just say, oh yeah, you can do that with a finite automaton. And you, in the club, might say, oh, do you mean DFA or NFA? And the answer will be like, this is kind of a red flag if somebody says this to you in the club. Because the answer is like, it doesn't really matter. Anything you can do with a DFA, you could also do with an NFA and the other way around. Because an NFA can always be converted into a DFA in this way. So as from an abstract point of view, NFAs and DFAs, of course, they are different. They have different rules and whatever, but their power as computing machines is the same, because you could always any NFA you could convert into DFA and vice versa. So they are not expressing different computational power. They are two different ways of modeling the same sorts of things. All right, I think that'll do for today. We'll have our quiz next time, but then we'll do some more examples like this. The subset construction.